Welcome to the Deep Dive. Today we're plunging into something really core to industrial automation, CNC controllers.
Yeah, the brains behind the machines.
Exactly. And we're going deep into their architecture. We've got this great article by Dr. Hovsepian in Smart Industry Magazine, Part 3 specifically. It talks about embedded, PC-based, and hybrid systems.
It's a really good breakdown of the fundamental structures.
So our mission here is to figure out how these design choices, the architecture itself, impacts things like stability, precision.
Flexibility, how long they last out in the field.
Right. The article calls it a harmonious symphony, which I kind of like. Every part connected, playing its role. So maybe let's start there. Why is the architecture such a big deal? Like the conductor, you said.
Yeah, something like that. It's fundamental, this choice, the architecture. It really sets the stage for everything else. How stable is the system? How accurate can it be? Can you adapt it easily? How long will it even function reliably? It directly shapes the machine tool's performance, how it handles tough industrial conditions. So yeah, it dictates how well that machine performs its job day in, day out.
So it's not just what it does, but the how it's built from the ground up. And Dr. Hovsepian outlines three main ways: embedded, PC-based, and hybrid.
Yeah.
Different, right? Performance, flexibility.
Exactly. Very distinct characteristics and suited for different jobs.
Okay, let's tackle the first one then. Embedded architecture. What's the story there?
Right, embedded. So think of this like all the control tasks are baked directly onto special dedicated hardware. And critically, they use real-time operating systems, or RTOS.
RTOS. Okay. Not like the Windows or Linux we use every day.
No, exactly. No general purpose OS. Instead, you've got these light, really stable industrial processors. Things like ARM Cortex-R, maybe Intel Atom, or specific microcontrollers.
And they look different too.
Often, yeah. They can be pretty compact modules, sometimes without even a screen or interface directly on them. They're designed for one thing: super reliable tasks, tight timing, and running for a very, very long time, like a marathon runner maybe, built for endurance and precision.
That makes sense. So the strength is that focus, like a specialist?
Pretty much. The article highlights very high operational stability. They use resources efficiently, and the performance is predictable. Even if the factory floor is hot, vibrating, dusty, these things are built to handle it.
High precision, fast response, keeps going. Sounds ideal for production lines.
Definitely. Continuous production, where consistency is key.
But there's always a but, isn't there? What's the trade-off for all that dedication?
Flexibility and scalability, that's the main one. Because it's so specialized, adding new features or changing how it works isn't simple. You usually need direct access to the hardware itself, the specific development tools for that platform. It's not like downloading an app update.
Right. So examples, the article mentioned some.
Yeah, things like the FANUC Series 0i, Siemens 828D Basic, maybe some Mitsubishi M70 models, or Ferrix 4B. These are workhorses. Super precise, very reliable, but not easily changed on the fly.
Okay, so embedded is the focus specialist. But what if you need that flexibility? What if you want something more like a regular computer? And that takes us to the PC-based approach, right? Which sounds maybe easier, but riskier.
That's a good way to put it. With PC-based architecture, the CNC functions are mostly software running on a standard PC.
Like the one on my desk.
Pretty much, yeah. It uses a general OS, Windows, Linux as the platform. That OS manages everything, moving the axis, controlling the spindle, the user interface.
So no dedicated industrial hardware, no RTOS.
Typically not, no. It relies on the standard OS for scheduling tasks. It's definitely a different philosophy. More like using a general purpose tool for a specific job.
What are the upsides then? Why go this route?
Well, flexibility is huge. Software development is often easier. You can connect peripherals more readily, and the initial setup costs can be lower. You get great software flexibility, it's easier to upgrade, and it handles complex graphics or data analysis tools better. It's very accessible, especially if you're developing something new or for, say, educational purposes.
But that reliance on a standard OS, we've all had Windows crash, right? How did that translate to a factory floor?
That's the Achilles heel, really, because it's not a real-time system and it doesn't have those layers of industrial protection. It's much more vulnerable.
Vulnerable to what, specifically?
Electrical noise, delays in response time. Performance can be unstable. Things that might be annoying on your desktop can be disastrous in high-precision manufacturing.
So probably not for building airplane parts.
Generally, no. It's not recommended for high-precision stuff or really harsh environments. You see it more in schools, small workshops, maybe running 3D printers or desktop CNCs, places where a slight hiccup isn't catastrophic.
Okay, so it's like the tinkerer's workbench, great for flexibility and cost, but maybe not for the mission-critical production line. You mentioned playing with fire.
Yeah, if precision and absolute reliability are paramount in a tough environment, PC-based can be risky.
So we have the super stable, dedicated embedded systems and the flexible but potentially less stable PC-based ones. How do you get the best of both? Is there a middle ground?
There is, and that's the hybrid architecture. It's designed specifically to try and combine the strengths of both.
Okay, the best of both worlds approach. How does that actually work in practice?
It's pretty clever, actually. It divides the tasks. The really critical, time-sensitive stuff like controlling the exact position, speed, motion of the axes that gets handled by specialized industrial processors or FPGAs,
FPGAs.
field programmable gate arrays, basically hardware you can configure for specific tasks. And these components run with a real-time operating system, just like the embedded systems.
Yeah.
That ensures the speed and reliability for the core machine control.
Got it. So the critical parts get the dedicated real-time treatment. What about the rest?
The less time-critical tasks, managing the user interface, running complex calculations for the path, data analysis, reporting those are handled by an industrial PC, an IPC, or maybe a more powerful general processor.
Ah, so it uses the PC's strength for the complex software side, but keeps the motion controls separate and robust.
Exactly. You get the accuracy and dependability of the industrial hardware where it matters most, plus the software flexibility and power of a computer for the interface, connectivity, and higher-level functions.
What are the main benefits then? Increased efficiency.
Yes, increased efficiency, better scalability because you can often upgrade the PC part more easily, and potentially lower costs for maintenance and upgrades compared to a purely embedded system that needs a full overhaul.
And the article mentions some examples here too.
Leading controllers like the Siemens Sinemeric 840Di, Heidenhain TNC7, or the Ferex F32, these are prime examples of mixing that industrial reliability with PC flexibility. It's often the choice for high-end, demanding applications that also need advanced features.
Okay, so choosing the right architecture. It sounds like a really crucial decision.
Yeah.
Not just technical, but strategic.
Absolutely paramount. You can't just pick one randomly. It has to be based on, well, what exactly does the machine need to do? How complex is it? What level of accuracy is required?
And the environment too, right? You mentioned harsh conditions.
Definitely. What are the working conditions like? High temps, vibrations, dust? And of course, what's the budget? All these factors play a role. So yeah, the big question becomes, how do you actually make that call for your specific situation?
Can you give us some examples? Like for different industries?
Sure. Take heavy industry automotive, aerospace, steelmaking. Machines there often need extreme precision, and they're working in tough environments.
Okay.
In those cases, stability and real-time response are non-negotiable. A tiny delay could ruin an expensive part. So you'd almost always go for an embedded or a hybrid system, particularly one with a strong RTOS-backed real-time section. That guarantees reliable, delay-free motion.
Makes sense. And what about, say, lighter applications?
Well, for educational settings, R&D labs, or maybe less demanding industrial tasks, where absolute top-tier precision isn't the only factor, PCB systems can be a good fit.
Because of the cost and flexibility.
Exactly. Lower costs, easier to program and experiment with. So for you, the listener, it boils down to really analyzing the specific needs and priorities. You're looking for that logical balance between performance, accuracy, cost, and how flexible you need it to be. Finding the right tool for the job, essentially.
So looking ahead,
Yeah.
Where are things going? What's the future look like for CNC controller architecture? Are new technologies changing the landscape?
Oh, definitely. Things are moving fast. We're seeing much more integration of advanced tech. Think powerful multi-core processors, a wider use of those FPGAs for custom processing right in the hardware.
More power, basically.
More power, yes, but also more integration. Systems on chip or SoCs are becoming more common, packing lots of different hardware and software functions onto a single chip. This lets controllers handle more complex tasks simultaneously, faster, and more accurately. They're getting smarter, not just faster.
And what about those big trends we hear about everywhere? AI, IoT, are they impacting CNCs?
Hugely. We're seeing a big push towards integrating edge AI and the industrial Internet of Things, IoT.
Edge AI, so intelligence right on the machine itself.
Exactly. Processing data locally, near the source, instead of sending everything to the cloud. This, combined with IoT connecting everything up, means controllers can analyze data in real time, get immediate feedback, and make smarter decisions on the fly.
So machines that can optimize themselves.
That's the direction. Smarter decisions, faster responses, using real-time data. It's moving beyond just control to intelligent participation in the whole production process.
Any other big trends in the architecture itself?
We're definitely seeing that trend towards hybrid and modular architectures continue. Modularity is key, being able to swap out or upgrade parts like the computing module or the I/O without replacing the whole system. That offers huge flexibility and cost savings over time.
And connectivity.
Massive. There's a growing need for controllers to talk to everything else. Other machines, factory management systems, cloud analytics platforms. So architectures are moving towards more open standards and really advanced communication capabilities. The controller is becoming a central communication hub.
Wow. So it really feels like we've gone from dedicated boxes to these incredibly complex, connected, almost intelligent systems.
It's a major evolution.
So wrapping this up, we've really dug into these core architectures,
Mhm.
the dedicated precision of embedded, the flexibility of PC-based, and that powerful blend in hybrid systems. It's clear understanding these isn't just technical detail, it's key to grasping modern manufacturing.
Yeah, and that final thought from the article really resonates, doesn't it? That combination of real-time control, software flexibility, and serious processing power that's shaping the future. A future of smarter, more autonomous machines hitting peak performance with less direct human input.
It really makes you think. So for everyone listening, consider how knowing about these architectural choices might empower you. Whether you're deep in manufacturing, doing research, or just want to understand our increasingly automated world, seeing the symphony inside these machines. Well, it's more than just interesting. It feels like a vital piece of understanding where industry is heading.